Hey everyone, it's time for us to talk more about the feasibility condition. The feasibility condition is the process by which our EIGRP speakers are going to determine which prefixes can be installed in the topology table. So what I'm going to do is I'm going to right now defer any conversation about the routing information base and the adjacency table. And what we're going to do is we're going to look specifically at the idea of this topology table. So the topology table. Now, the topology table is going to be a listing of the prefixes and the sources that we're learning those prefixes from. So in other words, what's going to happen is for every route we learn, we're going to have entries in our topology table. Then what's going to end up happening is we'll do our computation against the topology table to determine which prefixes are going to be installed in our RIB. Now, I want to illustrate that a little bit better than what we've done so far, because what I want to do is I want to walk through this idea of the feasibility condition, or the feasibility condition. What is it, first of all? Well, we've already illustrated the point that if I look at the contents of my routing table for the prefixes that we're looking at, notice I have my metric, which is 2195744 and 219744. Since these two are equal, I'm going to put both of these in my routing table. But what happens if these are unequal? Well, if these prefixes or if these entries are unequal, first of all, we have to decide whether or not they're both going to be included in our topology table. Now, prefixes that are incorporated into the topology table meet what's referred to as the feasibility condition. And here's what the feasibility condition is. Notice, here we don't really see anything other than our metric. Now, what we have to recognize is that we have two metrics. We have the feasible distance, which is going to be what we refer to as our actual metric locally. And then we also have another concept called the advertised distance. So here's the deal. So this device, R1, is advertising a prefix. Well, this unit, Cat1, learns that prefix, and what it does, it assigns a cost to it, or a metric to it, based on those two values that we talked about, bandwidth and delay. So what happens is it's going to increment what it learns. The value after the incrementation, after I add my bandwidth and my delay computations to it, is referred to as my feasible distance. The information that R1 advertised to me and said, this is what I use to reach this prefix, is referred to as the advertised distance. Now, when we take these two particular components and we add them up, or we look at them, what ends up happening is if the advertised distance of our neighbor is less than our locally computed feasible distance, then what ends up happening is that this particular prefix can be installed in the topology table. That's really and truly all there is in the feasible condition. The feasible condition simply states that if the advertised distance of my neighbor to reach a prefix is less than the feasible distance that I would use to reach that particular prefix, then I can place that in my topology table. And the reason that I can do that is because if it's less for that, if it's lower for that device to reach that particular prefix, then I know that that loop does not go, that particular path does not go through me. Therefore, since the advertised distance is less than my feasible distance, what ends up happening is I know that particular route is going to be loop-free in nature. Now, what I want to do is I want to super simplify our topology. I'm going to turn off bandwidth computations. So when we go into this, we need to understand how we're going to do that. Well, remember, we have this notion of our K values, where K1 is the coefficient that magnifies bandwidth, or this idea of throughput, and K3 is the idea or the coefficient for our delay value or our latency. Throughput and latency making reference to named operation. So what we'll do is on this particular device, I'm going to turn off our computation that uses bandwidth. So I'm going to say config T router EIGRP 10. I'm going to say metric weights 000100. hold on here, metric, I forgot to type weights. Now that's going to kill my connection, which means I need to do this on every device. So what we'll do is we'll go through this very quickly and we'll mark each of these off. So we did R22. So next what we need to do is we need to do R2 and R3. So let's cut over to them and do that. R2, config T, router, EIGRP 10, metric weights 000100. And we'll do R3, router, EIGRP 10, metric weight 00. Remember, TOS is always 0. We're turning K1 off. K2 is always off. We're leaving K3 on. And now we set that. That should bring our metric back, our unit back up. But what's going to happen is we do not get our connection back with Cat1 and Cat2. So let's go over to Cat2 first. Do the same thing. Router, EIGRP 10, metric weights 0001. Actually, no, that's wrong. So it's TOS 0, K1 0, K2 0, K1. That should bring our link up. We have a new adjacency. So let's go over to K1 or Cat1. But what are we doing here? Show, run, section, router, EIGRP. Well, notice right here, we're running named mode. So we're operating in router, EIGRP named operation, and we're using this idea of the IP address family to be able to do our configs. So the question now is where do we make these configs? So let's go and do this. Let's say config T, router, EIGRP, named, address family, IPv4, autonomous system 10. Now inside here, notice I have the metric value here. So I could type metric weights 0, 0, 0, 1, 0, 0 and press enter. That should bring my link back up to R2, which it did, but my link to R1 is going to be down. So let's go over to R1 and make the matching config. Config T, router, EIGRP named, address family IPv4 unicast. You can specify unicast. If you leave it off, it'll by default apply unicast. Autonomous system 10, metric 0, 0, 0, 1, 0, 0. And that should bring everything up. We should get a connection with Cat2 and Cat3. Oh, metric weight. I did it again. This should bring everything up. And we see we have a new adjacency. So if we got all of our sums right, I'll go ahead and clear everything off of this part of the console. We should be able to go back over to the data center router and see if we can do load sharing. So what I'll do just very quickly is I'll just do a trace route, and we can see now we're going through R2 and R3. But let's take a look at these prefixes now. So if I do show IP EIGRP topology table, notice what's happening now is our metrics are now substantially smaller. Our metrics are less than 1 million. And the reason being is even though we have this idea of bandwidth configured, we're not using it for our metric computation. Now the reason I did this is the fact that yes, even though everything is the same, because we have the 2 serial connections, 1 on each link, and then everything else after that is Ethernet connections, I just merely wanted to remove all of the components that could cause us problems and consternation with regard to trying to manipulate the paths across our infrastructure. So let's take a look at this. Now, first of all, we see that our metrics are the same. Now, this is the advertised distance. So I am learning from R2 that its feasible distance to reach the network 11.11.0.0/24 is 2588. That's its feasible distance locally. but it's advertised to my device as an advertised distance, which we see right here. Now, all I want to do is I'm going to go over to R2, and I want to illustrate that point. So on R2, I didn't mean to do that. Bear with me just 1 second here. So on R2, show IP route 11.11.0.0.255.255.255.0. And what are we going to see? Notice here is my feasible distance. Now that means that's what I've added, but the question is what is my neighbor Cat 1 telling me it is? Well, let's take a look at our table. Show IP EIGRP topology for 11.11.0.0/24. And what do I see? It's telling me that it's 288. So this value right here is the feasible distance on Cat 2. 288. Now what I'm doing is I'm adding my own value to that to come up with this 25,888, but that's my feasible distance. So when we start taking a look at this, it's important for us to understand, lastly, what R1 is reporting. So that means the feasible distance that's being reported is going to be seeable on R1. So let's take a look at Cat 2 first. So what I want to do is I want to see 288 as the feasible distance on Cat 2. I'm sorry, on Cat 1. Show IP route 11.11.0.0.255.255.255.0. And what do we see? We see our metric is 288. So that's exactly what we expected. Our route metric is 288. That was the advertised distance that or Cat 2 reported. And lastly, let's go over to R1 and see what R1 has. Actually, let's stay on Cat 2, Cat 1 just for a second. Let's take a look at the topology table. Show IP EIGRP topology table for 11.00/24. And we can see that it's reporting a value of 32. So on R1, the feasible distance is going to be 32. Show IP route EIGRP, show IP route 11.11.0.0. And we see our distance here is, first of all, it's connected. So notice I'm not seeing anything in here, connected. So let's take a look at the table. Show IP EIGRP topology for 11.11.0.0/24. And what we're going to see here is there is no advertised distance, and the composite metric that we're using here is 812920. Now, let's not get confused there, because remember, we're using picoseconds for our computation on this particular device. Keep in mind, named mode and our classical mode EIGRP won't necessarily marry up 100%, but we could go through here and we could take a look at exactly what's going on with regard to the computation, but we've already reviewed that process when we discussed named operation. You can go ahead and just follow those formulas to pull out that information, and you should be able to reverse engineer what the actual advertised metric is. Keep in mind, when we looked at the traces, when we looked at the Wireshark outputs, we saw that our devices were simply reporting the information about what's considered to be the legacy metrics. And then based on whether or not a device is configured as named or as classic, what happens is the device is then going to take that information, it's going to use it for its own local computations. So keeping in mind, again, the fact that we have that difference of operation. Now, what I want to do is I want to entertain this idea of the feasible condition. So I'm going to go ahead and take all of this off, and what we're going to do is we're going to track the prefix 11.11.0.0/24 from R1. First of all, what we're going to do is we're going to track it as it travels this way, and we're going to do all of the math for the computation. On this side, I'm going to use 11, actually, I'll use via R2, and on this side I'll use via R3. Now, the devices that we want to work with here are going to be R1, Cat1, and R2, and lastly, R22. Here it's going to be R1, no, hold on, it'll be, what am I doing, R2, oh, through R2, through R3. So it's going to be from R1 to Cat2. From Cat2, it's going to go to R3. From R3, it's ultimately going to arrive at R22. Now, when we take a look at this, what we want to do is, since we turned bandwidth off, all we need to look at is the delay values. So let's take a look at what happens. And what I'm going to do is I'm going to go to R2 on the link connecting it to Cat1, and I'm going to change the delay. First of all, let's look and see what that delay actually is already. So on R2, what is the delay? The local delay. Show interface E02. Now, when I go in and I look at this, what do I see? I see my delay is 1,000 microseconds. Now, what I'm going to do is I'm going to change that. So I'm going to say config T interface E02 do show CDP neighbors, just to double check and make sure that that's exactly what I want. 02 is connected to, so it's 03. 03 to Cat1. Didn't think that was right. So do show interface E03. Let's make sure that our values are right. 1,000 microseconds. Now what I'm going to do is I'm going to change this value here. I'm going to say delay. And what I can do is I'm going to enter this through, but remember I need to put it in tens of microseconds. So right now we know it's 1,000 microseconds. So if I put it in tens of microseconds, I just remove 10, and I'm going to put it in tens of microseconds. Now what I want to do is I want to change this. I'm going to say I want it to be 2,000. Now that means I'm going to put in 200 tens of microseconds right here. So let's do that. Let's say delay 200 and hit enter. Now what this should do is it should affect our computation. Now what I'll do is I'm going to go ahead and remove this, and I'm going to annotate what we did up here. On this link we changed it to 2,000 microseconds, or 200 tens of microseconds. Now let's see exactly what happens here on R22. So let's look at this. First of all, let's just go ahead and repeat it for the topology, and let's see what we have going on here. Well, let's see. What do we have going on? So from R2, did we change anything? Well, notice it's 537,888, and here notice it's 563,488. So notice the values are now different. The path through R2 is now 363, where the path through R3 is now 35788. Now the beauty of this is the fact that these entries are still both in the routing table, in the topology table, but what we need to do is we need to ask ourselves, based on this output, which of these prefixes are going to be installed in the routing table. Now let's look at this. When we go in and we take a look at it, we know that the lower metric is going to be the prefix that normally gets installed. So I'm going to bump up a little bit, and what I want you to see right here is notice it says we have one successor. And the feasible distance of that successor is 537,880. Now, when we look at this, what we're going to do is we need to address the feasibility condition first. The feasibility condition states that we will not place a prefix in the topology table unless the prefix is equal to our own, or if it matches the feasibility condition, which means the advertised distance of our neighbor must be less than the feasible distance that we use to select our best route. Now in this scenario, what we see is our feasible distance, I'll go ahead and take myself out of the equation here, my feasible distance equals 537,888. And that's going to be learned through serial 2/1. Notice that's it right here. Now, the other part of this is can I install the second prefix in my routing table? Well, let's look at what's going on here. So what did I say? I said we could place it in the table provided the advertised distance, in this instance it's going to be through S20. So the advertised distance from this device to us says it is 514. Oh, man, I'm all over the place. Sorry about that. Go ahead and just make it all look pretty. So through serial 20, the administrative distance that we're learning is 51,488. If this value here is less than this value here, then this means that this prefix can be installed in our routing table. So let's take a look at what's going on now. I'm sorry, it can be installed in the topology table. But remember, what's going to happen is the metric is going to determine which route is placed in the routing table. So what I'm going to do is I'm going to grab this rack here, and let's just go ahead and do a trace route to 11, 11, 0, 11. And what do we see? We're not traversing through R2. Why? Because the only computation that we have running in our metric calculation is delay, and the delay is higher through this link than it is through this link here. So what's happening is that we're picking R3 for transit. Now, the whole idea of this conversation is to talk about the concept of unequal cost load sharing. Now, what I want to illustrate here is the fact that we can only do unequal cost load sharing provided we have the routes in our topology table. So irregardless of what we do with regard to unequal cost load sharing, the variance command, which we're going to be talking about in the next part of the presentation, irregardless of how high that value is, what's going to happen is that it will only allow us to do unequal cost load sharing via links that are installed in the topology table, because only the links that are in the topology table are the links that we know are going to be loop free. So with that being said, what I'm going to do is I'll see you guys in the next part of the presentation, where what we're going to do is we're going to take these unequal cost paths and we're going to actually use them for the purposes of load sharing. So I'll see you guys in that presentation. Bye-bye.